Today we're going to continue on the following of the episode 3 with the episode 4, and we're going to talk about some information that was missing on episode 3. First, there was a little error of typography about the formula for the probability of exactly k-men choosing their own hats p and k, with p and k being equal to k choose n times n minus times the factorial of n minus k times p of n minus k 0 over factorial of n. We need to understand combinations. To determine the number of subgroups of 3 men from a set of 5 men, we use the combinations 3 choose 5, which is described below. It says that the result is 10, because 5 times 4 divided by 2 equals 10. Thus, there are 10 subgroups of 3 men among a group of 5 men. Now, if we list the subgroups, we can show that if the men are represented by the letters A, B, C, D, and E, for instance, the subgroups of 3 men among these 5 men can be listed as ABC, ABD, or ABE, ACD, and so on. So there are, as expected, 10 distinct subgroups of 3 men among 5. Now, the difference between combinations and arrangements. The definition of a combination is it is the number of subgroups of k elements from a set of n elements without considering the order. It is denoted Cn(k) or k choose n. What is an arrangement? It is the number of subgroups of k elements from a set of n elements considering the order. This time, denoted A and k, it is also the number of injections from 1k into 1n. What are the formulas? The formulas are, for the combinations, factorial of n over factorial of k times factorial of n minus k, and for the arrangements, almost the same thing. It is the factorial of n over the factorial of n minus k. For instance, for a set of 5 elements, the arrangements of 3 elements are calculated as factorial of 5 over the factorial of 5 minus 3, which is equal to 120 over 2, which is equal to 60. So, there are 60 possible arrangements of 3 elements from a set of 5 elements. The differences. Combinations. The order of elements does not matter, so the ABC group is the same as BAC. On the contrary, when we look for arrangements, the order of element matters. It does matter this time. So ABC is different from BAC. For instance, you can see in the following example, for combinations of 3 elements from A, B, C, D, E, we have the 10 following groups. For arrangements of 3 elements from A, B, C, D, E, here is a subset of the 60 possible arrangements. So you can see that we have ABC and ACB with the green arrow. They are different. And we have also ABD that is different from ADB, which would not be the case if we look at our problem with combinations. Same thing goes for ACD and ADC, and for ABE and AEB. Conclusion: combinations are more relevant than arrangements in problems where the order does not matter, such as the hats problem. Using combinations avoids unnecessary complexity and focuses on the essential groups of elements. When looking at 3 choose 5 equals 10 times factorial of 3, which is equal to 6, it gives us the result 60, which is also the factorial of 5 over the factorial of 5 minus 3. So, to understand this formula, k choose n, it is simply the number of subgroups of 3 elements among 5, the number of subgroups of 3 men we can create among 5 men, times the number of permutations per subgroups, the number of way you can rearrange the group of 3 men, your group of 3 men. And that gives you the number of arrangements of 3 elements among 5. So all the possible arrangements of your 3 men among a group of 5 men. So subgroups, the number of subgroups, and you multiply this by the number of permutations possible per subgroups. The hats are, in our problem, the hats are mixed randomly, and the order does not matter. Once mixed, what matters is only which men find their hats. Adding order with arrangements will complicate the problem without providing new relevant information. Combinations allow us to focus on the groups of men who find their hats, which is the objective of the problem. The arrangements 1, 3, 5, 1, 5, 3 will be treated as being different, while they represent the same situation. Men 1, 3, and 5 find their hats. So it is the same thing as the men 1, 5, and 3 find their hats, or the men 5, 1, and 3, or 5, 3, and 1, and so on. All of this explains why we have k choose n combinations in our formula Pn of k equals k choose n times factorial of n minus k times Pn minus k 0 over factorial of n. Like we said, for 3 men among 5 to choose their hats correctly, there are 3 choose 5 equals factorial of 5 over factorial of 3 times factorial of 5 minus 3 equals 120 over 12 equals 10. Possibilities only, and then we have to look among these possibilities what choice is left for the rest of our 5 men. For now, we only say that there are 10 ways for 3 men to pick their hats, if it happens. Like always, the others are left with factorial of n minus k choices to wrongfully choose their hats, and for the choice to be wrong, we need to multiply by p of n minus k 0, the probability of 0 men choosing their own hats. And so that's all for today. I hope it clarifies a lot of things from the previous episodes, and see you soon with more interesting content. Goodbye.